Welcome to a two-part series on chemical equilibrium. Well, let's first start out with the concept of equilibrium. At this point, we've looked mostly at chemical reactions as one-way processes, starting with reactants and ending with products. However, most chemical reactions are not that way. As a reaction progresses, there's a buildup of products which causes the reverse reaction to occur. And when the forward rate and reverse rate are equal to each other, a dynamic equilibrium is established. So as you can see in the graph here, over a period of time, the concentration of the reactant goes down and the concentration of the products goes up until such a point as each levels off. That is where equilibrium occurs. As a result of that, we get the following. The Kf is the rate constant for the forward reaction times the concentration of the reactants equals Kr, which is for the reverse reaction, times the concentration of the products. So we're going to look at a reaction below. We start with only N2O4, which is a colorless gas, and it breaks down into NO2, which is a brown colored gas. And over time, the concentration of NO2 decreases, N2O4 decreases, which we can see right here in this line, and the concentration of NO2 increases, which is the now upper graph. But starting at about here and going forward, the concentrations of each stay about equal. And we get flat lines. That indicates that we are now at equilibrium. We can look at this reaction in a different way. We can start out with NO2 and produce N2O4. And again, we see at a certain point of the reaction as it moves forward, the concentrations of each, the reactant and the product, are in equilibrium, and they do not change over time. The reaction quotient is a ratio of the concentration of the products to the concentration of the reactants, each raised to a power equivalent to their stoichiometric coefficient. This is not the same as what we are working with the rate law. Just to remind you, in the rate law, you had to experimentally determine the exponents. So for a hypothetical reaction of A plus B goes to C plus D, the reaction quotient is concentration of C to its power, concentration of D to its power. In the denominator, the concentration of A to its power and B to its power. It's very generic, so I guess we have to look at some examples. So here we are. We got two reactions here, and we need to look at the reaction quotients for each of these. In the first reaction, QC is the product, which is AgNH3, doesn't want to do that twice, and the concentration of that, and there's only one of those. And in the denominator, you have the concentration of Ag and the concentration of NH3 squared. For reaction B, the quotient is concentration of NO2 squared over the concentration of NO squared and the concentration of O2. In the bottom half of this slide, we can use the quotient to write a reaction. In this case, we have oxygen and ozone. The reactant is in the denominator, so we have O3, and the coefficient 2 gives us the stoichiometric coefficient, and that is in equilibrium with O2, which is in the numerator, and the coefficient there is 3 from the exponent 3. For reaction B, the reactants are cadmium 2 plus 4 bromides makes this cadmium bromide complex. When the system reaches equilibrium, our reaction quotient is represented by the equilibrium concentrations of the products over the equilibrium concentration of the reactants, and because they are stable over time, we call this the equilibrium constant, and the equation is called the equilibrium expression. So we can use equilibrium concentrations to determine the equilibrium constant, and later we'll see that we can use the equilibrium constant compared to the reaction quotient to determine if a reaction is actually at equilibrium. Calculating equilibrium constants, we have to do a number of experiments. Well, this is chemistry, we do experiments. So in the experiments below, we get an average equilibrium constant of 0.00463 molar from the reaction of N2O4 decomposing to NO2. The equilibrium expression is given as Kc equals concentration of NO2 squared at equilibrium divided by the concentration of N2O4 at equilibrium. In the first reaction, we see that there is no product. It's all reactant to start out with. So as a result, we have to form some product. And what I'd like to show you is that the value of the QC and the KC will tell us a little bit about the direction things are going to move. In this case, the KC is greater than the QC, and the arrow basically is telling us that the reaction will go to the right when the Kc is greater than the QC. Well, let's see what happens when it's the other direction. In experiment number 5, down at the bottom, we have no reactant. It's all product. The QC is undetermined because the denominator is 0. And thus we have in this situation that the Kc is less than the QC, because it's basically infinite, and the reaction has to proceed back to the reactant because there is none. Again, following the arrow. Well, is this true in other situations? Well, let's look at the one in the middle, reaction 3, where the concentration of N2O4 is 0.5 molar and the concentration of NO2 is 0.03 molar. The QC is 0.00180. So I'm going to put up here the Kc 0.00465, and over here 0.00180. And as we can see, the Kc is larger than the Qc, so the reaction has to go forward. That is, we're going to lose reactant and gain product. Well, let's see if that happens. Here's the reactant, loses concentration. Here's the product, gains concentration. Now let's look at the magnitude of the equilibrium constant. There are three possible outcomes of a reaction, and the equilibrium constant tells us a little bit about that. Reactions that essentially go to completion, that is, all the reactants become products, the value of the equilibrium constant is usually very large, greater than 100. In some reactions, they are much larger than that. For reactions that basically don't go very much at all and produce extremely small amounts of product, the Kc is usually very small, less than 0.01. And finally, those are those that are between the two. The reactions that are between them tend to be mixtures of both products and reactants. When we get to studying reactions that involve electron transfer, that is redox reactions, we will find that the reaction constants for those that do proceed in the forward direction can be as large as 10 to the 5th, 10 to the 6th, and higher. Reactions that don't go are reverse reactions of those that do, and the reaction constants of those are extremely small, 10 to the -5th, 10 to the -6th. Very few of those reactions have an equilibrium constant that is in this middle zone where there's a balance of reactants and products when we study redox reactions. I should probably make some changes to this slide, because as I showed you before on a previous slide, the arrow, or the greater than, less than arrow, will indicate the direction that the reaction will go if you put the equilibrium constant first and the reaction quotient second. Then in this case, the Kc would be less than the Qc, indicating there are more products than the reactants, and the reaction will proceed backwards, as in a less than sign. And at the bottom, we would have the Kc is greater than the Qc, and the reaction would go forward, as in a greater than sign pointing to the right. Here we have a reaction. Carbonyl chloride, also known as phosgene, is made by reacting carbon monoxide with chlorine gas. At 74 degrees Celsius, the equilibrium constant is 220 per molar. The concentration of the compounds are as follows: carbon monoxide, 0.25 molar, chlorine, 0.050 molar, and carbonyl chloride, 0.15 molar. Determine the direction the reaction must go in order to reach equilibrium. So to do that, we need to write the reaction quotient, the Qc. So Qc is the concentration of the products, COCl2, divided by the concentration of the reactants, CO and Cl2. And then we have to put their numbers in there. Don't go under the false assumption that because 0.25 and 0.05 are less than 0.15 that it has to go back to reactants. Don't fall for that one. What we're looking to see is Kc greater than Qc? So we'd proceed to the right, or is Kc less than Qc? It'll proceed to the left, or are they about equal? So it's close to equilibrium. Well, let's put the numbers in there. In the numerator, we have 0.15. In the denominator, we have 0.025 and 0.050. And when you finish with that calculation, what you end up with is 120. So 220 is greater than 120. So the reaction needs to proceed to the right. That is, it needs to make more product so that the QC will increase in value and become closer to the Kc, that is, equilibrium. So this is one of those cases where if you just looked at the raw numbers, they would confuse you as to the actual situation. Next, let's look at what is called heterogeneous equilibria. Solids and liquids that are in separate phases from the rest of the reaction have concentrations that basically remain constant. Since those concentrations remain constant, we can remove them and multiply them into the reaction constant or the equilibrium constant, and therefore they will not show up as part of the reaction quotient or the equilibrium constant. So in this reaction, carbon dioxide plus carbon makes 2 carbon monoxide. The carbon will not show up in the reaction quotient or the equilibrium constant because it is constant. Well, let's write the equilibrium expressions for the following. In the first reaction, mercury in the liquid state reacts with the mercury 2 cation to make the mercury 1 cation. Because mercury in the liquid state has a constant concentration, the equilibrium expression will be the product of the mercury 1 at equilibrium divided by the reactant mercury 2 at equilibrium. In the second example, we have oxygen as a gas plus 2 hydrogens as a gas, making water as a liquid. So the equilibrium constant is the products over the reactants, but the products here are in the liquid state, so we don't have a concentration for the water, and the reactants, the oxygen at equilibrium and the hydrogen at equilibrium squared is the equilibrium expression. when the reactants and products are gaseous, the equilibrium expression can be expressed in terms of the partial pressures of the individual gases. So for example, in the reaction above where N2O4 decomposes into 2NO2, the Kp, because of pressure, is the partial pressure of NO2 squared divided by the partial pressure of N2O4. And we can also derive a relationship between Kc and Kp using the fact that the ideal gas law can put pressure in terms of molarity, and that is pressure equals molarity times RT. Substituting partial pressures with molarities, we find that the Kp is equal to the Kc times RT. And the relationship between the two is Kp equals Kc times RT raised to the power of delta N, which is the number of moles of gaseous products minus the number of moles of gaseous reactants. So, for example, in the reaction of N2O4 making 2N2O, the Kc is 0.00463 at 25 degrees Celsius. What is this value of the Kp at the same temperature? Well, we simply stick in Kc, and then we put in RT, and R is the gas constant in liter atmospheres per mole Kelvin, with the temperature converted to Kelvin, and the delta N is 1 because there are 2 product molecules and only 1 reactant molecule. Thus, the Kp is expressed in atmospheres, whereas the Kc is expressed in molarity. For the reaction to make phosgene, COCl2, the Kc for that is 220 molar at 74 degrees Celsius. What is the value of Kp at this temperature? So, what we have is Kp equals the Kc times RT to the delta N, which equals 220 molar times RT, 0.082056, times the temperature in Kelvin, which is 347. And the answer is, before we finish the calculation, the delta N is minus 1 because the number of moles in the product is 1, the number of moles in the reactants is 2. So the delta N is minus 1. So basically what we're doing is we're taking 220 and dividing it by RT, 0.082056 times 347, and the answer to that is 7.73 atmosphere, minus 1. Manipulating equilibrium expressions. In this first one, all we're going to do is reverse the reaction. So we're going to take A plus B and make 2 C's. So K1, the equilibrium expression, equals concentration of C squared divided by the concentration of A and the concentration of B, which is 2.34 times 10 to the negative fifth. If we reverse the reaction, the reactants become products, products become reactants, and therefore the denominator of the previous equilibrium expression becomes the numerator, and the numerator becomes the denominator. In effect, we've taken the whole equation and turned it upside down. Therefore, the new equilibrium constant, K2, is simply 1 divided by K1, which equals 1 divided by 2.34 times 10 to the negative fifth, giving 4.27 times 10 to the fourth. In this next manipulation, we want to have 1 molecule or 1 mole of C produced rather than 2. So we divide the entire equation in half. So we have half of an A and half of a B to make 1 C. As a result, our equilibrium expression is C divided by concentration of A to the 1/2, B to the 1/2, which is equivalent to the square root of K1 for its value, and the square root of K1, 2.34 times 10 to the minus fifth, equals 4.84 times 10 to the minus third. Our next one is to double everything. We have a new equation, C goes to D plus E. If I want to double everything in this reaction, the 2C makes 2D plus 2E. I'll have to take the equilibrium expression of equilibrium 4, K4, 9.87 times 10 to the sixth, and square it because all the unit values are squared. Concentration of D squared, concentration of E squared divided by the concentration of C squared. So K5 is 9.87 times 10 to the 6th squared, which is 9.74 times 10 to the 13th. Now we're going to combine equilibrium 1, which produces 2C, and equilibrium 5, which takes the 2C and makes it 2D plus 2E. Now remember that equilibrium 5 was the square of K4, and the equilibrium of K1 given previously was 2.34 times 10 to the minus fifth. So to go from A plus B to 2D plus 2E, we have D squared E squared over A times B. And if we put C squared in the numerator over A and B, and then C squared in the denominator underneath D and E squared, basically you see that the combined equilibrium constant, K6, is K1 times K5, which is 2.28 times 10 to the ninth. Now it's time to work a few additional problems. The two equilibria that we're working with are 2NO plus O2 makes 2NO2. Kc equals 6.9 times 10 to the fifth per molar, and H2 plus O2 makes 2H2O, the formation of water, and the Kc equals 2.4 times 10 to the 47th per molar. So let's determine the equilibrium constant for the following. 2NO2 makes 2NO plus O2. Well, if we look above, it is simply reaction 1 in reverse. Being reaction 1 in reverse, then the value, we'll call this K3, equals 1 over K1, which is 1 over 6.9 times 10 to the 5th. And I'll let you do the calculating on that one. In this next one, we have 4NO plus 2O2 makes 4NO2. Again, that's reaction number 1, but this time it's doubled. So we'll say here K4 equals K1 squared. So that equals 6.9 times 10 to the 5th squared. And again, I'll let you do that calculation. On the last one, what we have is NO2 plus H2 makes NO plus H2O. We get the NO2 from reaction 1 by taking half of it and reversing it. So that's kind of tricky. So we have NO2 makes NO plus 1/2 and O2, and we've reversed it, so it is 1 over K1, but we've also halved it, so it is a square root of 1 over K1 for that equilibrium constant. The other part is to take H2 plus 1/2 O2 to make H2O. This is half of reaction number 2, so the reaction constant is the square root of K2. When we add the two reactions together, this half O2 cancels and we get the net overall reaction, and K5 equals the square root of K2 divided by K1, which is 2.4 times 10 to the 47th over 6.9 times 10 to the 5th, and the square root of all that. Once again, I'll let you do that calculation. Le Chatelier's principle uses the application of a stress on a system at equilibrium so that it is no longer at equilibrium. This causes the system to shift as a way to minimize the stress and restore equilibrium. The following can stress a chemical system at equilibrium: addition of reactant, addition of product, removal of reactant, removal of product, change in concentrations or partial pressures due to change in volume, change in temperature. The addition of reactant puts pressure on and causes the reaction to move to the right to produce more product and to reduce stress. The addition of product causes the reaction to move to the left to reduce stress. Removal of reactant causes the equilibrium to shift left to reduce stress. The removal of product will cause it to shift right as a result of the removal of product. Change in concentrations or partial pressures due to change in volume depend upon whether there are more product molecules or more reactant molecules. And finally, the change in temperature. As we saw before, temperature affects the equilibrium constant by affecting the rate constants. So its effect is on the Kc or the Kp via the rate law constants for each of the different reactions. In this problem, we're going to look at the addition of a reactant. I'll take hydrogen and react it with iodine to make 2 hydrogen iodides. The Kc is hydrogen iodide squared divided by hydrogen and iodine, and it's 54.3. Previously calculated, the equilibrium concentrations were the following: 0.22 molar for hydrogen, 0.321 molar for iodine, and 1.958 molar for the hydrogen iodide. Determine the direction after the addition of 0.1 moles of hydrogen to the reaction in a 1 liter container. So we're going to increase the molarity of hydrogen to 0.321 molar. And now the calculation of the reaction quotient is 1.958 squared divided by 0.321 squared, which is 37.2. 37.2 is less than the current Kc, so the reaction has to proceed to the left. But if we looked at it from the previous mention that I gave, that if we put Kc first and determined if Kc is greater than Qc or not, in this case, Kc, which equals 54.3, is greater than Qc, which equals 37.2. And I'm going to use the arrow here as an indicator that the reaction moves to the right toward the products. In this next problem, we're going to add some product. So starting out with the same initial concentrations at equilibrium as the previous problem, we're going to add 0.2 moles of the product, hydrogen iodide, to the reaction container, which is 1 liter, which increases the concentration to 2.158 molar. So calculating the Qc, we find that it's 65.6, and thus comparing the Kc to the Qc, Qc being 65.6 and Kc being 54.3, now the arrow points to the left, indicating that the reaction will proceed to produce more reactant molecules. So the previous two were addition of a reactant and then addition of a product. Now we're going to determine what happens if we remove. First is we're going to remove a reactant, then we'll look at removing a product. So we're going to remove 0.1 moles of iodine from the reaction in this 1 liter container, which reduces the molarity to 0.221. And the calculation for the value of the reaction quotient ends up 78.5. With this, Kc, which is 54.3, is less than Qc, which tells us that the reaction is going to proceed to the left, giving more reactant. Removal of product. This time we're going to remove 0.2 moles of the hydrogen iodide from the 1 liter container to get 1.758 molar. Putting that into QC. QC calculates to be 43.6. So comparing that to KC, KC will be greater than QC. As a result, we would expect the reaction to proceed to the right. Increasing the volume in a gaseous reaction is equivalent to adding solvent to an aqueous reaction, because it will change the molarities. Given this reaction, 2 nitrogen dioxides in equilibrium with N2O4 at 25 degrees Celsius, the Kc is 170. We're going to calculate the Kp and look at it from that point of view. So the equilibrium pressures in a 1 liter flask come out to be: the partial pressure of nitrogen dioxide is 0.200, and the partial pressure of the dinitrogen tetroxide is 0.278 atmospheres. We are going to then change the volume of the flask and make it a 2 liter container and determine which way the reaction will proceed to reestablish equilibrium. Well, if you remember back to your gas laws, pressure and volume are inversely related. So if I double the volume, I'm going to divide each of the pressures in half. So the pressure of the NO2, the new pressure, is 0.1 atmospheres, and the new pressure of the N2O4 is 0.139 atmospheres. When we finish the calculation, we find that QP is 13.9, and comparing that to the KP above, so KP is 6.95, is less than the QP here. When we increase the volume, causing a dilution effect, the reaction will proceed to the side that has more molecules, in this case gaseous molecules. So we're reestablishing the equilibrium in order to fill that space again, and to do that you have to increase the number of molecules, and the way to do that is to go, in this case, from products to reactants. If the reaction was the other direction, N2O4 going to 2NO2, then the reaction would proceed to the right, producing more NO2 gas as you increase the volume. The same effect occurs in dilution in aqueous solutions because the molarities change. Molarity and volume have the same relationship as pressure and volume in gases. That is, they are inversely proportional. Decreasing the volume in a gaseous reaction. Now we're going to look at this same gaseous reaction as in the previous slide. The Kp is 6.95. We're going to decrease the volume, so we're going to take the volume from a 1 liter flask to a 0.5 liter, And as a result, the partial pressures will double. Volume is half, pressures double. So now we're going to put the doubled pressures into our calculation of the reaction quotient, and that comes out to be 3.48. The relationship between Kp and Qp in this problem is that the Kp is greater than the Qp, telling us that the reaction will be driven toward the side which has fewer gaseous molecules. Decreases in volume will go to the side with fewer gaseous molecules. The effect of temperature on an endothermic reaction. Remember that in an endothermic reaction, heat has to be added. So we'll consider heat as a reactant. So by adding more heat in increasing the temperature, we're going to shift the equilibrium to the right. So we can think of it as adding a reactant. Adding heat to an exothermic reaction, the heat is considered as a product. So by adding heat, we're going to drive the reaction back toward the reactants, just as if we were considering adding a product to a reaction mixture. Well, that's Le Chatelier's principle and the end of this PowerPoint.